I guess this is a keynote, so I want to start with a bigger vision, but the general keynote is really about kind of like, I guess, my 5 to 10 year vision of like how I imagine compiler design, but then enriched with a lot of like very recent work, either completed or there's a lot of like ideas that we are exploring. So I hope that it's somehow inspiring. And I took an example a little bit outside of the compiler work that's kind of like really inspiring, I hope, which is kind of the reference of moonshots. So these moonshot projects, kind of these 10-year visions you want to deliver. And in the space industry, I guess a lot of you heard this quite famous Elon Musk, SpaceX, obviously always dreaming big and sometimes more big than realistic. But one of these projects that recently starts launching is the Starship, which is a space craft which should bring us to Mars, and which is also the spacecraft that kind of enables internet anywhere on the globe. And though I guess even in kind of like programming language and compiler dimensions, these are rather large goals, right? And so I want to use 5 minutes to look a little bit into kind of like, well, not compilers and programming languages, but space industry. And so what really made these kind of big moonshot visions possible is this radical change in cost of constructing rockets. So for almost 50 years, shipping a kilogram kilogram object into space was around 25K, and around 2023, it should be down to around $200 per kilogram, which is orders of magnitude cheaper than before, right? And this is these kind of like radical change in production cost that enables radical visions in space travel, right? And so the question is, how was that possible, right? And so classical rocket engines really were designed very differently. They have 1 to 3 engines per rocket, a very small number. They're highly specialized, extremely optimized. But because they are so special, you can build one of them per year. So it's a heavily manual production. And right in space, or at least what the SpaceX company does is they take, like, construct or use 30 engines per rocket, and they are all small, exchangeable. And because they are building so many, they really reach a rate of like 350 engines per year. So you can automate things, and that accelerates the design, makes it a lot cheaper, and you can experiment a lot more with these things. So why do I talk about this? And the reason is I want to remind you a little bit how we build different software in our software ecosystem, right? How do we build compilers? How do we build SMT solvers? How do we build interactive theorem provers, verification engines, DSL code generators, EDA tools? How many intermediate representations do we build and construct per compiler? I guess for almost all of these projects, it's more or less a single-digit number of intermediate representations, maybe 2, 3, if we are lucky, but rarely. I mean, we rarely construct a new intermediate representation more than every decade, I would guess, right? So we're really slow in this aspect, I would assume. And in particular, there are a lot of boundaries between these tools. So whenever we want to build a compiler that interacts with a code generation framework, or so I didn't have another error, but if we want to build an EDA tool that needs to be verified, each time we cross these boundaries and we need to convert between representations, right? And I want to take you into one specific project, tensor comprehension, for example. That's a project built around my background, polyhedral compilation. It's a domain-specific compiler where you use affine loop transformations to accelerate deep learning benchmarks. It doesn't really matter what it does. We know, well, there are certain loop nests. We rotate them using a mathematical abstraction, and then in the end we get large speedups, right? So we have a domain-specific compiler, and we get speed up in this compiler. The polyhedral compiler, tensor comprehension, well, actually, it's not even a polyhedral compiler. in some way it was very unique that it actually managed to reuse a lot of components, right? So it has this like polyhedral representation or like user facing Einstein notation, very simple. Then it uses halide as a project for image processing, and the halide IR. Then it uses a polyhedral intermediate representation. Then it uses LLVM. It uses A10 expression language. So basically, it uses 5 different IRs, which in some way, I think is a big achievement because it heavily reuses existing ecosystems, right? So in some way, like was seemingly quite easy to build this domain-specific compiler just by stitching together existing components. But one of the main takeaways or lessons learned here is, even though there is a lot of reuse, there's an immense cost whenever we convert along these errors. So these IRs are heavily redundant. They're not really compatible. So most of this project, or a large portion of this project, was trying to stitch components together that don't really fit well together, right? So there's interfacing is very costly. There's a lot of complexity, and it's very lossy in this particular project. Another project here is very much like a kind of a Huawei project. Again, we have many IRs. So some of these modern DSL compilers really have a high-level operation, a compute IR, polyhedral IR, highlight IR again, CUDA code. So again, like 5 IRs stitched together. They seemingly work perfectly together in practice. I think there is a high conversion cost. And so I want to use this keynote to introduce a project that was started by Chris Lutner a couple 2 years ago, just to give you a little bit an overview. But here the key idea really is to take the abstractions from LLVM, developed over 10, 15 years, and take out the specifics of a C or C++ compiler and really make it possible to instantiate an LLVM style IR very quickly. So the high-level story here is that there's a lot of redundancy in compiler pipelines. So C compiler translates to LLVM IR and then to x86 and different platforms, but various other compilers do the same thing. And in fact, most of them introduce their own IRs because it's often helpful to exploit high-level information. However, the question is, how do you build these IRs? And the kind of typical recipe in our communities was you take domain knowledge, you build a custom IR that is inspired by LLVM syntax and sometimes actually uses the LLVM data structures. And then you re-implement a lot of the default functionality that LLVM has: a parser, a printer, pass manager, dead code elimination, peephole optimizations, everything specialized to this specific custom IR. So all that is re-implemented, it's very costly, and in the end, you emit LLVM IR. So MLIR is really a project that tries to simplify this and tries to figure out how to avoid this cost. So one idea here is that we make this MLIR dialect declaration, a declarative specification, and then actually auto-generate many of these components. And in the end, that supposedly saves a lot of cost. How would that look like? This is LLVM IR. There's a function, there's an argument, there's a basic block, there's a phi node, there's a terminator instruction, the branch instruction here at the end, and there's an operation. So many of these concepts are shared across IRs. The Swift IR has very similar concepts. It looks slightly different syntax-wise. There's a different branch instruction here. There are basic block arguments instead of phi nodes, but overall it looks very similar. And so the idea really is, as we saw in this overview slide, to make an MLIR operation that can basically be instantiated to any specific domain. So an operation really consists of a result, an operation name, an argument list, and then a type. And if you instantiate these kind of very generic operations for a specific domain, then you can create something like LLVM IR, but also like something like Swift IR still, but also IRs for various different domains. And MLIR also has a block, just a sequence of instructions with a block name, instructions, instruction list, and terminator operation. And the nice thing is that in theory, at least, all of these abstractions could be implemented in a compatible way, kind of using LLVM quality all over the place. In fact, you could even represent instruction sets using the very same infrastructure. And obviously, many of these kind of domain-specific languages, as they are, that we've seen before. One of the key changes here is that we move away from this traditional single-dimensional compilation flow, where we really just lower from one high-level abstraction to an target instruction set, and we start to have IR abstractions that can be combined in multiple ways. So C++, then we can go to an AST where we maybe already optimize a standard vector, and then we may have a lot of like specialized instructions there that can all be specialized IRs that somehow represent different features, for example, in C++. So it could be something about OpenMP, something about loops, something about a library like GMP. And then some of these abstractions could actually be reused by a different pipeline, for example, a Python DSL, which directly connects to a linear algebra dialect. So that's quite interesting because we already see that we can use these abstractions to compose different compilers, bring more domain-specific information into a compiler. And different to the previous illustrations, these errors are actually quite easy. So these transitions are very convenient and don't have a lot of conversion cost. And so now we want to convince you a little bit that these abstractions are actually very interesting, even beyond the classical programming language ecosystem. So we looked before at this Huawei's Mindspore AKG compiler, which is a domain-specific compiler for tensor operations. And I have on top here the classical or the original design. And as with many DSL compilers, you can take these existing stitched together designs and try to re-implement them by combining existing or novel abstractions in this LLVM ecosystem or in the MLIR ecosystem. So for example, you could have a GPU dialect, which we published and presented at TACO recently. You can have a linear algebra dialect, for example, replacing the halide IR. You have kind of a standard and structured control for dialect for compute IR. And here in the middle for the polyhedral part, you can have an affine dialect and a math library. And so I invite you now to look a little bit into the math library. So there will be a more extensive talk at UPSLA about it. I go a little bit quickly about the key implementation and then show you a couple of ideas that are not yet published, but that might be quite interesting in that setting. So the idea of this math library is really to bring fast polyhedral computation directly into this MLIR project. And this fast polyhedral compilation really is this kind of like the key mathematical objects of this constraint-based loop optimization techniques in polyhedral compilation. We call it FPL. And very, very briefly, an introduction of what polyhedral compilation or press-program arithmetic, as we call it, uses as objects. And it's really about integer polyhedra. So integer points in a multidimensional vector space constrained by linear inequalities. And these objects are reasoned about again and again in polyhedral compilation. You can take two of these convex objects, you can unite them, and then you get a union of integer polyhedra, what we call a Pressburger set, and this is the basic object we reason about. Mathematically, these objects are quite easy. You can apply classical set operations over these polyhedra. So you can intersect A and B, can unite them, you can subtract B from A, you can complement A. You can check if one of these sets is empty, meaning it doesn't have an integer point, or you can sample, so get like one of the integer points in the set. There's also coalescing, which simplifies these sets. So this is, I guess, really a jump away from instruction sets or intermediate representations. And so maybe it's not immediately obvious why I talk about these kind of math libraries in this workshop, but I hope we'll get there soon. So there's some interesting to say about how to optimize them. So all these constraints are actually just matrices, 2D matrices, where the columns represent the dimensions of your vector space plus a dimension for the constant dimension. And so the entire processing of this library modifies these integer polyhedra represented as matrices. So this is a computational concept. You take a matrix, you apply an operation, you get a new matrix as an output. And so in our paper, and I go very quickly about this, we optimized this, we got a lot of test cases, figured out that we can exploit certain opportunities, and in particular that the values are small and low dimensional. The matrices are low dimensional, and then we specialize for that and get a fast library. So I go quickly over this because if you want, you can listen to this talk at Uppsala. You get nice speed up. But what I want to talk about is this is kind of a vision, something that hasn't really neither been published or not discussed. But the interesting thing here is that polyhedral compilation really works over, applies operations over these integer sets or Pressburger sets, right? So MLIR as a tool could actually be used to represent these operations, right? Union just takes two sets, returns a new set, intersect, subtract, complement, equal, exactly the same. We could model contains, so check if one set contains another or if one set contains an element. But we can also use this representation of these expressions, for example, to simplify expressions before we even compute them. In this case, the unite expression is redundant because we computing the union between twice the same set is obviously redundant, so we can eliminate that instruction, and we can do that at compile time, which is quite nice because that allows us to solve simpler problems when we actually go towards the matrix or constraint representation. Double complement, we can eliminate the double complement. It's also just an identity, so we can remove both of these operations, which can be asymptotically faster. Or we can try to evaluate these instructions, right? So we can start to constant propagate over these Pressburg operations, which again, this can be simplified. So overall, we can perform some transformations already on the IR level, which is quite interesting. And what's now also interesting is this invention of kind of, or like this ability to design cross-domain compilers. So in this case, for example, we may want to generate code that evaluates some of these properties. So for example, we can translate this Pressburger IR into LLVM IR or standard dialect in MLIR, which actually results in imperative code that evaluates for a certain value of X and S if S is within X. So I think that's quite an interesting way to kind of use MLR as a tool to really bridge different domains. And I want to jump very much to a different topic, which is hardware design. And here, I want to briefly introduce you to a project called LLHD, and then recently the Circuit project, which is based on a PLDI publication that Fabian, Andreas, and Luca and I published in 2020. And here the story is very similar, even though the software ecosystem is very different, or at least today rather disjoint. And similar to the MLIR motivation story, where we had a lot of software compilers using shared compiler abstractions, the hardware ecosystem actually looks very similar. So in the hardware world, most people program in System Verilog or in VHDL. Some more esoteric languages, or at least less widely used languages like Chisel, Spinal HDL, some HLS tools, or some other hardware description languages kind of provide higher level language interfaces to Verilog, but in the end, they all compile down to Verilog. And then the interesting thing about the hardware design stack is that it's heavily redundant. So there's a simulator which has its proprietary compiler, proprietary optimizer. There's a synthesizer, again with a proprietary compiler, a proprietary optimizer, a logical equivalence checker, or a verifier. And again, what's interesting here, and some of you may have followed LLVM and then some of the open source compiler ecosystem, and in fact, most of the C++ compilers 10, 15 years ago looked very similar. Right? There's almost any hardware vendor, Intel, AMD, but also software vendors like Microsoft, they all had their own C++ front end, they had their own C++ compiler to target their own hardware. And eventually what's here, this redundant piece became LLVM. Today, what we say is we want something like LLVM, kind of a shared open source infrastructure for hardware. And then what we came up with is this LLHD compiler. So it's a low-level hardware description language, which can be targeted by a front end called MLIR from System Verilog, which can be lowered from behavioral to a structure layer, which can be passed to a simulator, and which can be shared by all these different tools, right? And I want to introduce a little bit to LLHD and make the case that this is indeed just another abstraction that one can implement for MLIR. So that can be used as a shared compiler intermediate representation, in this case for hardware design. And yeah, LLHD can also be the result of a synthesizer, so it can encode the lowest level net list that you use to eventually actually produce your hardware. So we go here a little bit more quickly. It's not necessary that we understand the details of this System Verilog code in the end, but I want you to get an impression of the flow that happens in LLHD. So we start here with the System Verilog code at the top, and then we use MLIR to translate it into behavioral LLHD. And so I now go a little bit slower to give you an opportunity to look at the LLHD intermediate representation. We don't need to understand in detail, but I want to give you the opportunity to try to identify concepts that may look familiar, in particular if you are used to LLVM, and concepts that are new, right? So for example, we have here basic blocks, or labels that label basic blocks, sequences of instructions, another basic block check, another basic block event. So this is quite classical. We have a couple of arithmetic operations, an and, a not equal, which is also quite classical. We have types, 1-bit integers here as well. But there are a couple of things that are new. So for example, we have new instructions, a probe instruction that probes what's called a signal, and a drive instruction here at the bottom, which drives what's called a signal. And then we have new types, I1 $, where the dollar identifies the signal type. So as we see, a couple of operations, a couple of types are new in LLHD or different to a classical compiler IR, but overall the structure is very similar. We also have now different kind of functions. We have an entity, we have a process, and we'll have some more later on. But what you see now is really that overall, if you want to actually describe a piece of hardware, you can use a very similar textual representation. In fact, a very similar tooling infrastructure to reason about these kind of descriptions. So now what actually happens to simplify is that we just run a couple of standard compiler transformations, dead call elimination, constant sub-expression elimination. So this starts to simplify these programs a little bit. Then there's a couple of more hardware-specific transformations, which we use here to eliminate most of the control flow. And that's basically what a system Verilog compiler typically does. It takes code that is behavioral, so it has control flow, transforms it into structural control flow, structural LLHD, a program or hardware representation which doesn't have control flow and which you can actually synthesize on a chip. So now we lower here to what's called an entity. We do some more optimizations, often actually, again, classical compiler transformations, just using a slightly different set of operations. And what we have is basically a compilation flow that is open source. It follows more or less the ideas of LLVM, but instantiated for the hardware ecosystem. And I think just last year, we worked with Xilinx and Sci5 to actually turn this into an open source project, which is now available at circuit.llvm.org. It contains LLHD as one part, plus a simulator, plus an entire stack for Fertile and Chisel, which is a more higher level, higher productivity language to target hardware. And as you see, again, we start to share components. So there's a shared RTL abstraction. There's a Verilog emitter. And hopefully more and more of these code can be shared. I want to zoom into a little bit into the simulator, just again to make the case that hybrid IRs, so moving between IRs across vastly different tools in a compiler or in the actually systems ecosystem is quite interesting. So LLHD sim is about simulating hardware, right? So to simulate hardware, you need three components. You need a simulation engine, you need an execution of a particular component of your hardware, and then you need to simulate the trace that you get from this unit execution. So in the end, what you build is an event-driven simulation. You have all these units living independently, and they send messages among each other. So when there's process, in your event-driven simulation, you basically have an instance on LLHD, which consists either an entity of a process. And you have time steps. So each of these messages sent has a timestamp, which is basically a signal in the LLHD world. So wherever there's a signal, these are the channels over which messages are sent. And then you get a set of incoming events which have a certain latency, and you know that there's a certain order between these events. And this order obviously needs to be preserved. Yeah. So you need to sort them, and then basically that happens all just in time while you execute or simulate your program. The question is, how can we generate fast code for that? And so what you have is an event queue. Basically, you start to initialize your simulation. You pick the earliest slot in your queue. You update the global simulation time. You update your signal values. You wake up all the kind of sensitive instances, all the instances that are affected. Then you execute them, see if they produce new events, put them in the queue, and pick again the next earliest event. So basically, you ping pong between looking up an event in the queue, updating signals, running the relevant instances, and collecting new events. And so the way we do is actually, it's quite simple. We just take an LLHD module or an LLHD abstraction, convert it into LLVM, and then run the LLVM and the MLIR execution engine to get a JIT compiled representation of that program. And that's again interesting because we have again these kind of cross-domain tool here where we start with a hardware layout and we get we translate very quickly to an imperative program. And that's quite nice because it can be described easily and kind of this conversion cost. And because we reuse a shared infrastructure is actually really low. To illustrate that, I just show a couple of very simple examples. So an LLHD entity and an LLHD process just become LLVM functions, which have state tables, global, local state tables, and a signal table. And the same thing, a constant is an LLVM constant, an XOR is an LLVM XOR, and a negation is basically a lowering due to the operations that are available in LLVM. So this is really straightforward and quite easy to implement this component of a high performance simulator. Some of these operations are more complicated. For example, this driving a register actually involves control flow. So we can go through this a little bit. So we first evaluate here this branch, and basically to compute the input values, we have multiple cases, one for a falling edge, one for a rising edge. I don't have a picture for that. But basically, it's slightly more complicated, but in the end, it's a quite straightforward rewrite from one instruction to a sequence of instructions or operations on the kind of like imperative IR side. Then you get a simulation trace. We go a little bit faster over that, just that you get a feeling. So whenever you simulate that, what happens on the fly is that we will build this LLVM IR module, run it in the JIT compiler, and then we print the simulation trace. And so in our case, we actually, this is quite interesting for this was just a student project, didn't take very long, but we get an equivalent trace to a kind of a production quality tool. It's not a one-on-one match. This is a lot more debugging, kind of like more low-level details to be done. But the main takeaway is that this was, I guess, 2 or 3 months student project, where you really can write a simulator for system Verilog by translating from LLHD to LLVM IR. And the main thing you really need to do is to write conversions between these two IR abstractions. And what's even more interesting, I think, is the performance evaluation. So what you can see here is that basically Vivado is state-of-the-art, a kind of a commercial product. And we had multiple instances. LLHD Place was our kind of hand-coded like simulator before MLIR even existed. And in MLIR, we also re-implemented this very same simulator, which both MLIR, the simulator, and LLHD Place are in the order of magnitude of the Vivado simulator, whereas what's called the LLHD reference simulator really is a simulator that interprets the behavior of this hardware circuit without actually lowering to LLVM. And then you see a naive implementation of that simulator is a couple of orders of magnitude slower than state-of-the-art. But as soon as we lower properly to LLVM, we are basically in the same order of magnitude as a state-of-the-art simulation engine, which I think is quite interesting. And again, for implementing something competitive with a commercial product, quickly and kind of robustly, this rewriting across abstractions, IR abstraction, has been really, really useful. And so there's a lot more work that could be done in that space, where really, and I think that's again like one of the takeaways I want to send out. It's really about like developing abstractions and then combining these abstractions, right? So for instruction set verification, for example, we could have an abstraction for sale, which is Cambridge's verification language or specification language for instruction sets that would still need to be developed, and we could connect it to an RTL abstraction, maybe have a logic abstraction here in the middle, SMT solver logic, and then basically these boxes together could give you an instruction set verification tool. Maybe there's a cache synthesis tool. So where we take protogen, for example, we translate it to a state machine, and then we compare to different, translate to RTL if we want to synthesize hardware, or to Murphy if we want to simulate it. Similarly here, we can do pipeline synthesis. So we can take a pipeline model, a timing model, a sale abstraction, and translate it to RTL. And again, this might give us a tool to synthesize a CPU pipeline. Another tool that one could think of is a simulator, for example, that's a lot faster than the classical simulator, because the classical simulator works on RTL level. A specialized simulator like Verilator allows to work only on the kind of lower right-hand part of this hardware stack. But one could think about actually building simulators that cross all these levels and then simulate anything that can be simulated at a high level, at that level, and only kind of go to the low-level RTL simulation when actually needed. Many of these projects, could be done. Many of them are open. And yeah, I think we're back at this kind of like idea of a world of abstractions. What we really have in this world is today these boundaries, boxes, partitioning the different tools. And I think what I really expect to develop over the next couple of years is this ecosystem of IRs that somehow roughly belong into the different boxes, but which we really can kind of connect and reassemble to build interesting tools. I want to mention a little bit kind of the process of community building, because I think it's quite important in that ecosystem, because maybe let me say one or two more words here in that space. Building abstractions is useful, but if we go back towards the rocket, the main objective really is to make this a commodity. So making building abstractions easy and allowing connections between abstractions to be established as quickly as possible, right? And with as little effort as possible, right? And so for that, community building is really important. And now I want to use one slide to suggest and inspire what I call the construction of open communities. So what I see often in research is this kind of isolated research. So we have an in-house research and development team working for 2-3 years on a project. They release code. They, at the very end of the project, they ask for feedback and want to upstream it or share it with the community. And what typically happens is that a community doesn't trust these kind of large code wraps that research teams sometimes release. And they have a lot of questions, so many questions typically that this sharing and upstreaming of code gets to a standstill. Students graduate, and then this project kind of remains at the state where it was. And so I suggest really to think about like open research, and that's a little challenging because we talk about projects that haven't been completed, but really announcing a project early on, get a lot of code reviews. I work a lot in the LLVM and MLIR ecosystem. We typically review and commit our code directly to LLVM, and we want to motivate external people to join, external people to collaborate, and then different companies, different people would exist even if students leave. And so I think this is one of the main takeaways. How do we build this ecosystem together? Can we do that as a community? And I guess this is most of my talk. I want to finish with two more slides, kind of a sneak preview of what's happening. One is, again, this abstraction game. So building compilers, SMT solvers, verification engines, DSL code generators, and EDA tools. And one of the ideas that is currently discussed and developed, partially public, partially not yet, in the MLIR ecosystem is to not just have abstractions for different domain-specific IRs, but in fact have abstractions for meta IRs. So an IR to describe the rewrites on other IRs, and an IR to describe the definition of an IR. So on this slide, what you see here is an IR for complex arithmetic, multiplication, followed by multiplication, followed by computing of a norm on objects of type complex, right? And so on the left-hand side, we define an IR. In fact, we define two IRs, one called the complex math IR and one the implementation IR. The complex math IR has one type called complex and two operations, the norm and the multiplication. And then there's the implementation IR, which has another operation kind of to define the actual like memory structure of these complex type. But the main takeaway really is that I don't think we have, or like I want to go in detail through these different IRs or different rewrites, but the main takeaway really is this snippet of code is enough to fully describe and instantiate the different variants or a compiler that can parse and represent a complex IR and eventually lower to LLVM. And this part on the second side is enough to represent the rewrites. In this case, the norm of a product equals the product of two norms, right? And so one of the challenge in this compilation game, as I call this slide, is really to reduce the cost of instantiating these abstractions and the connections in between. And so in MLIR, there are two tools that are currently just developed. One is this IRDL representation, which we didn't talk about a lot publicly yet, and the PDL representation, which is already upstreamed in MLIR. So overall, like we hope that this will accelerate the design of dialects. And I also want to kind of share some very, probably 2 or 3 week old data on the number of abstractions that are available in the MLIR ecosystem today in the public repositories, and how much of these abstractions we believe can be defined fully declaratively. So there are overall 27 domain-specific IR abstractions, or as MLIR calls them, dialects, available in MLIR. LLVM is one of the biggest ones. SPIR-V is for some reason enormous, so they seem to have a lot of specialized instructions. And then there's a lot of smaller dialects, the GPU dialect for modeling CUDA. Interestingly, there's a dialect for PDL, the pattern description language itself, here for PDL and for the PDL interpreter. So it's kind of, we use dialects as meta dialects quite often. And what you can see is that for example, here for SPIR-V, around 30% of the dialect can be described fully declaratively. LLVM, almost all of it can be described fully declaratively, meaning just as this textual file. And other parts of the dialects, other operations require a little bit of C++ code still. So here quite a lot, here not so much. And this like medium blue part is really like just the verification of the IR, not actually the part that transforms the IR, but just the part that verifies the IR and asserts invariance requires C++ verification. And a very small part of these IRs actually requires more generic, like Turing complete C++ code to be described, which I think is quite promising, but there's also a lot more work to be done. But hopefully, like we can transition MLIR as a tool more and more towards a fully textual declarative representation for the large majority of its intermediate representations. And this is the latest data I have to share. I have a very last slide where I want to kind of advertise a little bit of a recent project that we started in Edinburgh, which we call efficient cross-domain DSL development for Exascale. And here the objective really is an instantiation of that talk for HPC DSLs in the Python ecosystem. So today there are existing DSLs in the climate space in the UK. Some of you may know, many probably not. One is called Cyclone. It's an embedded DSL for Python. It's a Python-based DSL to transform Fortran codes that implement climate reasoning or climate models. And DVito is a finite difference DSL for seismic imaging. It's an embedded DSL directly in Python. Both have a stencil abstraction and both target classical CPU, GPU targets. So they are highly successful in delivering like several petaflops of performance. So they really deliver on this kind of DSL promise of high performance, high productivity for developers and portability across platforms. But they are really isolated monolithic DSL stacks, right? So composability, interoperability, code reuse, and longevity of these projects is always a challenge. The same as like kind of the community challenges of the disjoint communities and like difficulties to transfer knowledge. And so in this XDSL project, we basically take this multi-level IR story and really instantiate it in 2 dimensions. One is the Python dimension. So really further lowering the cost of designing IR abstractions by not having to download MLIR and writing C++ code and and basically really going into the nitty-gritties of a compiler, but trying to understand if we can instantiate compiler abstractions purely from Python. And the second challenge is the introduction of domain-specific abstractions for the HPC domain. So we already in an earlier paper introduced the GPU abstraction to MLIR and a stencil abstraction. The MLIR community itself introduced OpenMP, a loop abstraction, and linear algebra. And there are a lot more abstractions that could be developed, for example, for more about tensors, about what's called an outer loop abstraction for some of the time loops in HPC codes, as well as key abstractions in Python like SymPy, NumPy, or like for message passing, like a classical HPC abstraction. And so the hope is really then that we kind of maintain the 3 positive benefits of DSLs, but get a lot more benefits around composability, interoperability, code reuse, and longevity. And in particular, solve this like knowledge exchange problem where communities don't interact, or maybe they interact, but at least their tools don't communicate. And yeah, I guess that's it. So I'd like to close with this slide, what I call the game of abstractions, or the compilation game. And I'm quite curious to hear feedback from some of you who listen to this talk. Thank you, everyone.